we're going to talk about null spaces and ranges. To do so, let's first review some concepts behind functions and linear transformations. Let's let x and y be sets. We use the notation f, x goes to y, to denote a function, where f lowercase x goes to lowercase y means f of lowercase x equals lowercase y for each lowercase x in the set capital X. The set capital X is called the domain of f, whereas the set capital Y is called the codomain of f. We can take a look at the range, or that is the image of f, as follows. Consider the set of elements lowercase y in the codomain y such that y equals f of x for some x in the domain capital X. This set is a subset of the codomain y. Similarly, we can take a look at the preimage or the inverse image of f. Given any subset U of our codomain capital Y, the set of elements x in the domain capital X says that f of x is an element of this set U is a subset of the domain capital X. Note that this f inverse is not a function. It's simply some notation to denote that we care about a certain subset of the domain capital X. Here we have a graphical representation of some of the concepts on the previous slide. The red on the left is our domain capital X. The blue on the right is our codomain capital Y. And the yellow, also on the right, is our range or our image of the function f. Say that we do have such a function f going from a domain x to a codomain y. We'll say that f is well defined if f of x1 equals f of x2 whenever x1 equals x2. For example, if we're mapping from the rational numbers to the real numbers by sending a ratio p over q to the numerator p, then we find a map that is not well defined. We can make this well defined if we simply add in the assumption that p and q are relatively prime. We'll say that a function is 1-to-1 if f of x1 does not equal f of x2 whenever x1 does not equal x2. Sometimes we'll call this an injection. For example, the function going from the real numbers to the real numbers that sends a number x to its square is not 1-to-1 because plus or minus 1 both map to the same real number plus 1. We'll say that a function is onto if for each lowercase y in the codomain capital Y, there exists a lowercase x in the domain capital X such that f of x equals y. Sometimes we'll call this map a surjection. As with the previous example, if we consider a function mapping from the real numbers to the real numbers, setting a real number x to its square, we find that this map is not onto. Indeed, there is no real number x such that x squared equals -1. Finally, we'll say that a function is both 1-to-1 and onto if it is an injection and a surjection. Sometimes we'll call this map a bijection. As a remark, we're going to reserve the word isomorphism for later when we talk about maps that preserve given binary operations. Given a well-defined map T going from some domain V to a codomain W, the following are equivalent. Here we're assuming that V and W are vector spaces. For all vectors x and y and v and all scalars c and f, we should have T to preserve vector addition, meaning T of x plus y is T of x plus T of y, and T preserves scalar multiplication. That is T of c times x equals c times T of x. This should be equivalent to saying that T preserves linear combinations. That is, given a collection of vectors v1 through vn and a collection of scalars a1 through an, we can consider the linear combination a1 v1 plus ... an vn. T should map that to T of a1 times T of v1 plus ... an times T of vn. A well-defined map satisfying either of these two is said to be a linear transformation. As an example, let's say that V and W are the real plane, R2. Then we can construct a linear transformation by using a 2x2 matrix whose coefficients are real numbers, as you see here on the screen. We'll now discuss the concept of null space and range. Let's introduce the following concept in order to motivate some definitions. Let V and W be two vector spaces over a common field F. And let's say that RT is a linear transformation going from V to W. Let's denote O sub V as the additive identity element of our vector space V, and O sub W as the additive identity element of our vector space W. Then T of OV equals T of OW. Next, let's consider the subset of the domain V that consists of those vectors x such that T of x is the 0 element in our vector space W. Then this set, which we're denoting by capital N of T, is a subspace of V. Moreover, our map T is 1-to-1 if and only if this set is the trivial vector space. Finally, let's denote R of T to be the collection of those vectors U in the codomain W such that U equals T of x for some vector x in the domain V. This set, R of T, is a subspace of W. Moreover, the map T is onto if and only if the set R of T is equal to W, the entire space. The set N of T, that is a subspace of the vector space V, is called the null space of T. Sometimes we'll call this the kernel of T. Similarly, the set R of T, which is a subspace of the codomain W, is called the range of T. Sometimes we'll call this the image of T. Let's discuss how to prove these three statements. We'll start by showing the first, that sends 0 elements to 0 elements. For any vector x of the domain V, we have the following. We know that our 0 element in V is simply equal to the scalar 0 times the vector x for any x in the vector space V. So, T of 0 times x is 0 times T of x, since our linear transformation is assumed to preserve scalar multiplication. But 0 times any vector is just the 0 vector, so staring at this identity in two different ways, we see that T of the additive identity of V equals the additive identity of W. Let's show the second statement in terms of the null space. In order to show that the null space is a subspace of V, we must show three statements. First, we'll show that the 0 element is in this set. Well, as we've just shown, T of the 0 element of V is equal to the 0 element of W. That means that the 0 element of V must lie in the null space. So, 0V is in N of T. Next, we'll show that the null space is closed under vector addition. Take two vectors x and y that are in the null space. Recall that what this means is T of x is the 0 element of W, and T of y is the 0 element of W. Now, if we were to take the sum of these, x plus y, and apply T to this, then we will find T of x plus y is T of x plus T of y is 0 plus 0, which is just the 0 element in W. Hence, the sum x plus y must be in the null space. Finally, we must show that the null space is closed under scalar multiplication. Let's take a vector from the null space, call it x, and take a scalar c. Since t preserves scalar multiplication, we can take t of c times x, and that is now c times t of x. But x is in the null space, so t of x is the 0 element of W. But c times the 0 element of W is just the 0 element. So we see that c times x must again be in the null space. Finally, we have to show the statement about t being 1-to-1 if and only if our element if and only if the null space is the trivial vector space. Recall we stated at the start of the lesson today that a map is one-to-one if and only if t is equal to y whenever x equals to y, only when x is equal to y. We showed that t is one-to-one if and only if the null space is the trivial vector space. First, let's say that t is indeed one-to-one. If x is an element of the null space, then we notice that t of x has to be the zero element of w by definition, but we just showed that the zero element of w is t of the zero element of v. This means that now we have t of x equals t of ov. So, since t is one-to-one, we must have x equals ov. This means that the only element of the null space must be the zero element of v. Conversely, let's say that the null space is just the trivial vector space. We'll have to show that our t is one-to-one. To this conclusion, let's pick two vectors x and y such that t of x equals t of y. Let's denote z as x minus y. Then t of z is simply t of x minus t of y. But now, since t of x equals t of y, we have t of x minus t of x, which is just 0. So this means that z must lie in the null space of t. By assumption, the null space of t just consists of one vector, namely the 0 vector. So this means that z must be the 0 vector, showing that x minus y is 0, so that we can conclude that x does indeed equal to y. We now show the third statement, that is, some statements about the range of t. In order to show that the range is a subspace, just like before, we must show three statements. First, we'll show that the 0 element exists in the range. Well, the 0 element is the image of the 0 element of v, so the 0 element of w must be in the range of t. Next, we must show that the range is closed under vector addition. Let's take two vectors u and v that are in the range. This means that u equals t of x and v equals t of y, so that u plus v is t of x plus y. Since x plus y is in the vector space v, we see that u plus v must be in the range. Next, we'll show that the range is closed under scalar multiplication. This follows very similarly from before. Let u be in the range and c be a scalar. Again, u equals t of x, so c times u is t of c times x. Since c times x is in the vector space v, c times u must be in the range. Finally, recall that a map is said to be onto if every vector u is in the form u equals t of x for some x in the domain v. It's now clear from the way we've set up our definitions that t being onto is equivalent to saying that the range equals the codomain w. Let's start here. Let's finish things today by discussing the dimension theorem. Say that v has a basis beta and w has a basis gamma. Then theorems 111 and 112 state that the null space and the range also have finite bases because they're subspaces. As a reminder, here is the statement of theorems 111 and 112. If v is a vector space with the basis beta and z is a subspace, then recall that z has a finite basis and the dimension of z is less than or equal to the dimension of the vector space v. We'll define the nullity of t as the dimension of the null space and the rank of t as the dimension of the range. The celebrated dimension theorem says that for any linear transformation mapping between two finite dimensional vector spaces, the nullity of t plus the rank of t is equal to the dimension of the domain. Some texts call this result the rank nullity theorem because it involves the rank and the nullity of a linear transformation. Let's sketch through the proof of this result. Say for the moment that our domain is a vector space of dimension n, and our nullity, that is the dimension of the null space, is equal to k. Since the null space has dimension k, let's choose a basis T for this space, it'll have k elements. Now I want to consider the following set. This will be the collection of those integers that look like they're the size of a linearly independent set beta that is contained in our domain V, but contains this set T. Using some ideas that we had from a previous lesson, we actually see that this set script P is a finite set. Every integer m in this set is between k, the dimension of the null space, and n, the dimension of the domain. Using the same ideas in this lesson, we can actually see that the largest integer in the set is n, so we can actually find a basis beta of V containing this set T. We'll also see this later on an upcoming homework set. Let's enumerate our set beta as V1 through V sub n. Remember that the first k elements must come from T, so we really want to consider the last n minus k elements. In fact, those elements, vk plus 1 through v sub n, let's apply T to each of those and form a subset S of W. We claim that S is a basis for the range R of T. In order to do so, we must show two statements. First, S spans the range. Here's why. Let's pick an element U in the range. This, of course, means that U equals T of X for some X in our domain V, but our domain V has a basis beta. So let's express our X as a linear combination of the elements from beta. We can now apply T, and recalling that T is a linear transformation, therefore it preserves linear combinations. We'll have a linear combination now of the vectors T of V1 through T of Vn. However, remember that the way we've set up all of this, T is a basis for the null space. This means that the vectors T of V1 through TV sub k must all be the zero vector in our codomain W. So staring at U here, we only have a linear combination left involving T of Vk plus 1 through T of Vn. But these are simply vectors in S, so this really means that our vector U from the range must be in the span of this set S. Next, let's show that S is a linearly independent set. To do so, let's say that we have an expression of the zero vector, perhaps involving some scalars b sub k plus 1 through b sub n. We'll take a look at the vector x that just takes a look at bk plus 1 times vk plus 1 plus bn times vn. This should be a vector that lies now in the null space of T. This vector x lies in the domain V. Now the null space we know is spanned by T, so this actually means that our x here must be a linear combination of the vectors from T. Putting this together, we have two different expressions for x, one involving b's, the other one involving c's. So we can take the difference, x minus x, to find the zero vector in our domain V. But this now is a linear combination involving the basis beta. Since beta is a basis, we see that each of the scalars in this expression must be zero. That is, there are no non-trivial expressions for the zero vector because beta is a linearly independent set by construction. This shows now that S is a linearly independent set, which actually means S is a basis for the range. So now we can simply count. The rank of T is the dimension of the range, but this, of course, is the number of elements in this basis S, which we just said was n minus k. N now is the dimension of our domain V, and k is the dimension of our null space N of T. So this means that the rank of T is equal to the dimension of V minus the nullity of T, which completes the proof. We'll give a very quick example of this since we do want to discuss more examples in the future. Let's consider now the real plane, and let's consider scalars so that we have now a linear transformation involving a 2 by 2 matrix. This we discussed at the beginning of the lesson today. The null space and the range are given by the following two sets. The null space is the set of vectors x, y in the real plane such that the transformation sends this to the 0 vector in R2, and the range consists of those vectors b1 and b2 such that t of x equals b1, b2 for some x and y in R2. If you stare at these in a different way, what we're actually doing are looking for solutions to a system of two equations and two unknowns. The system on the left involves finding points for the null space. The system on the right involves finding points for the range. Simply put, if we can find all solutions for the system on the left where everything equals 0, then we'll find the points in the null space. For the system on the right involving b1 and b2, all that we're asking is whether there does exist a solution. If one does, then the vector b1, b2 is in the range. If one does not, then that means the vector b1, b2 is not in the range. Thanks very much for listening today.